Today we will see about an video lecture series is heat conduction equation in spherical coordinates. In previous video we discussed about heat conduction equation in Cartesian coordinates and cylindrical coordinates. But in this case we will find out the heat conduction or the heat how to conducted in a spherical element. So consider this is a spherical element at the center and the radius of theta, pi and r. So in this case the heat conduction equation is from the previous cylindrical coordinates is we represented as the direction is dz, and here we will regulate the direction. So the equation of the heat flow is 1 by r squared dou squared by dou r squared in rt plus 1 by r squared sin theta into dou by dou theta in sin theta into dou t by dou theta plus 1 by r squared sin squared theta and dou squared t by dou theta squared plus q dot by k is equal to 1 phi alpha into dou t by dou t. So here is the alpha and q dot is will be in a heat flux with respect to the time t. So far the heat flow is only in the radial direction of a pi r is equal to minus ka dou t by dou r is equal to minus k 4 pi r squared dou t by dou r and the volume of 4 pi r squared into dr. Under steady state condition for a unit volume, dou pi r by dou r into dr is equal to q into volume of the spherical element is equal to rho c by k is equal to dou t by dou t. So the next that term is converted or moved into dou pi r by dou r is equal to dr is equal to 4 pi k 2r dou t by dou r plus r squared dou squared t by dou r squared into tr. So we multiply in this direction is 4 pi r squared k dr into 2 into dou t by r dou r plus dou squared t by dou r squared. So the dou squared t by dou r squared plus 2 into dou t by r dou r plus q dot by k is equal to 1 by alpha dou t by dou z for the steady state condition without heat generation. So this is the equation of the heat general equation is the condition of spherical coordinates. And the next we will discuss about the one-dimensional steady state heat conduction with heat generation. So the one-dimensional heat conduction equation we consider is a rectangular element, the or slab. The temperature of the output is in a TO with respect to the atmospheric temperature TW and the heat flux Q dot and the heat transfer coefficient K with respect to the length of the cylinder. So here is in a temperature distribution of the slab is Tx minus T naught divided by Tw minus T naught. So the term will be in the X is the thickness of the slab and L is the length of the slab of the square. So here we need to find about the X of the temperature in the slab is T naught minus Q dot by 2K in X squared and Tw is equal to T infinity plus Q dot L by H outside convection and Qx is equal to Q dot into X. So this is a solid cylinder. TO is equal to Tw plus Q by R squared plus 4K and the temperature distribution of the solid cylinder with the same as an a slab. For here we consider is in a x and here we consider is in a radius of r. So the slab is x directions and y directions and the distance will be converted into or distance will be measured by x. Here will be measured by the radius of r. So this is of the solid cylinder, and next we will go to the heat transfer conduction in without heat generation is a common basic formula Q is equal to del T by R. Here is the R is the resistance of the slab and here is the R is the resistance of the cylinder. So the slab resistance is L by Ka and the temperature distribution is X by L. Here is the cylinder resistance of R is 1 by 2 pi KL and ln of R2 by R1. Here is the hollow sphere is 1 by Rk and 1 by R1 minus 1 by R2. This is the temperature distribution of the hollow sphere. And the next one is in final cylindrical part is in we converted or we integrated the cylindrical part to heat transfer equation, and the final RD1 dy is equal to constant of the C1. Thank you.